Hello everyone, welcome to this tutorial. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to use Google Earth Engine Python API programming for the lake desiccation monitoring. I'm going to show you how to find your region of interest in the Python API and how to use XEE library to plot the lake variation over the time for the last 25 years. This tutorial could be very beneficial for those of you who are working in hydrological analysis and surface water bodies. Okay, let's go to the Colab environment and first of all try to import all necessary libraries. First of all, we need to import Earth Engine library because as you know, we need to make a bridge between Colab environment and Google Earth Engine code editor environment. So the next library is Xarray. The Xarray is a kind of library allows you to convert the raster and image collection to array structure that could be very beneficial for running machine learning analysis. Xarray as XR. The next one is NumPy. NumPy as NP. The NumPy is a library used for linear algebra. To apply the equation on the array structure, you need to use the NumPy. So the next library is matplotlib. Matplotlib.pyplot as PLT. The matplot library allows you to plot the outputs with the in the grid structure, same as this example I showed you. The matplotlib is a key library, allows you to plot the output in a good way. So let's run the necessary libraries first. Some of the libraries such as XEE not installed or it is not a built-in function in the Colab environment. So you need to install first. Install XEE, then import the XEE, just like that. So the XEE is a library that integrates Xarray and Google Earth Engine, and very beneficial to deal with satellite data in the Earth Engine using array structure. So all necessary libraries imported successfully without any challenge. The next step is related to make a connection between Colab and Earth Engine environment. From Earth Engine library already imported, start with authentication and then Earth Engine dot initialize the projects. The project name, the project refers to the Google Cloud project that is connected to your Earth Engine environment. If you go to the code editor environment, upper right here, you can see account information. Go to the project information and you can see your own cloud project name. For mine is this, Earth Engine, Amir Hussein Ahrari, my account name. So, but you must enter yours. The next one for XEE is OPTURL. This is the next argument we need to have for initialization, like this. Let's run it first, and now you have a pop-up. Click on your account and then continue and continue. Now the Colab environment successfully connected to the Earth Engine environment. In the next step, we can call the target satellite data. So make a new cell and go to the code editor environment. As we already connected to the Earth Engine, it is possible to call Earth Engine data catalog into the Colab environment. Go to search places and dataset and try look for Modis surface reflectance products. Modis surface reflectance products available with daily frequency or 8 days or multi-temporal data. I prefer to work with multi-temporal data because the temporal resolution, it doesn't matter with the high frequency in this tutorial, because the multi-temporal data actually provides higher quality pixels for estimation. 500 meter is the appropriate resolution for the lake monitoring. So let's click on this, and here through the collection snippet you can copy and paste the product information here. Make a new variable as modis and paste the image collection ID for the surface reflectance product. Then go to the bands to find the appropriate bands for this tutorial. So as you can see, various bands available here in visible and infrared region of a spectrum. So here we need to use near infrared and a near infrared and a green region of electromagnetic spectrum that help us to monitor the water bodies and calculate normalized difference water indices. Green and near infrared, both of them must be selected through the select function. So here just copy and paste the band names. Band number 2 as near infrared, band number 4 as green, both selected. Then you need to filter your data for a period of time you want to investigate in. So for example, this dataset available since 2000 to 2025. It is near real-time product. So let's start from 2001 to 2025. In this period, 2025 not included, I want to make an annual NDWI product that shows the water body over the Urmia Lake and see the lake desiccation in that region. So now only define the filter date and select the target band. I will show you how to find your region of interest in the XEE. So let's run a code, and now if you go to the variables, you can see the image collection already called through the Earth Engine library. So in the next step, we need to actually convert the MODIS image collection to a X-array dataset. To do this, make a new variable as ds equals to, okay, from X-array library already called, enter open dataset, just like that. If you go to the XEE tutorial page that is provided by Google experts and community, here you can see a complete instruction about how to call the satellite data with all the details. So as you can see in this instruction, first the image collection imported, then the engine to handle this data. Here it is, EE. The Earth engine actually, the EE engine provided by Google that allow us to use the X-array for image collections. So the next parameter, as you can see here, is related to the CRS and scale. If you want to have access to full resolution data, for example, the data resolution here is 500 meter. If you want to have this data with 500 meter resolution, it is important to define the CRS and scale. CRS coordinate system, EPSG 432826, sorry. This is WGS code, actually WGS 84 code that's used as a coordinate system for whole of the world. No matter in which area you are working. So if you want to have WGS84, actually the EPSG 4326 is a unique code. The next is scale. Scale equals to, the scale is spatial resolution or pixel size. The pixel size here defined based on a degree. For example, 0.25 means 25 kilometer. 1 degree, 100 kilometer. 0.1, 10 kilometer, just like that. And 1 kilometer is 0.01. That's here. This is 1 kilometer because 1 degree is actually 100 kilometer. 0.01 is actually 1 kilometer. There it is. I want to call this data with 1 kilometer. If you want to have actually 500 meter, then you can enter 10 or you can add 10 and 5. This is for 500 meter. It's totally up to you to use 1 kilometer or 500 meter. Actually, it's also depend on the size of area. As I'm gonna work on a big lake, actually 1 kilometer is enough and help me to have higher speed of processing in the high volume data analysis. So, and the next parameter is about the geometry. You need to define actually a rectangle for the region of interest and then bound your data to that location. Let's go to the code editor environment. In the code editor, you can easily find your region of interest. For example, I'm gonna work on Urmia Lake. This is one of the big salt lakes that actually are desiccating or actually faced with a lot of issues about the amount of the water bodies over the last years. And also that could be a good example for the lake desiccation here. So now if you want to select the Urmia Lake or any other lake you prefer for your own study, because this tutorial can be used for all around the world and not only limited to a region. So you need to have the coordinate of two areas, upper left and upper right. The coordinates of this region, upper left and upper right. Imagine we have a rectangle here. In this rectangle, two corners, upper left and lower right actually, their coordinates will help us to define a rectangle in the Python and then clip our region of interest based on. It is very important to clip your region of interest because it reduces the speed of processing, reduces the volume of data, and increases the speed of processing in the Colab environment. So here you can get help from marker tools or drawing tools available here. For example, the upper left corner could be here and lower right corner could be here, for example. So now as you can see, we have a new geometry here with two coordinates, the first point and the second point. We have a format for coordinates. For example, let me to make it a little bigger. That helps you to see the numbers and variables easier. So imagine I'm gonna make a rectangle coordinate here, rectangle. We have a format for the rectangle list here. For example, the location equals to, we have a list here, the minimum longitude and minimum latitude, then maximum longitude and maximum latitude. This is the format for the actually making a rectangle using 2 points. Let me to make it a little bit closer. No, it's okay, it's fine. So back to the map, and here, okay, here we have 2 longitude. This is the first, this is the second, and 2 latitude, this is the first, and this is the second. The mean longitude is this one, so 44. Just copy and paste it. Make a list and mean x or minimum longitude imported. Then minimum latitude. We have 2 latitude and this one is the minimum. Let's copy and paste it. Okay, then we go through the maximum longitude. The maximum longitude is here. Copy and paste it. And maximum latitude is also here. Just copy and paste it. It's very easy. Now the list for the rectangle is ready. Location equals to Earth engine dot geometry dot rectangle. We want to have a rectangle here. So the rectangle is ready. As you can see, it's a geometry. So now another argument as geometry added. Geometry equals to the location. Let's run a code. Let me to make it a little bigger. Okay, the problem here is about the geometry typo. So the geometry, now we are waiting to see the results. Hopefully the dataset is created. So here pay attention. The mod is actually the mod variable was an image collection, but now converted to a dataset with array structure. So here we have a multi-dimensional data, time, longitude, and latitude. Each one of these actually is a separate dimension that we can go through them part by part and easily and without any challenge. So in the multi-dimensional structure, 2 variables available, reflectance for band number 2 and band number 4. Let's make 2 separate variables for green and near infrared because I'm gonna calculate the near infrared and green band here. Green equals to, from dataset, from multi-temporal data, I'm gonna select the surface reflectance band number 4 is the band green. And if you go to the data properties here, you will find a scale factor that should be applied on each band before further processing. The green and near infrared created. From dataset, select surface reflectance band number 2 multiplied to the scale factor. Let's run the cell and go to the new one. 2 variables, green and near infrared, actually here created. As you can see, the near infrared, this is about the near infrared, for example. You will have an array of values, surface reflectance available for a whole period of time from 2001 to 2012 with 8 days frequency. And also here you can see the array structure or array coordinate of region of interest. Okay, now for all the dates, near infrared and green excluded. In the next step, I'm going to calculate the NDWI without any challenge, without defining any loop or something like that. NDWI equals to get green subtracted from near infrared divided to green plus near infrared. There it is. Now the NDWI for each date calculated. Make a new cell, get a print from NDWI. You can see the NDWI values with a temporal information, latitude, and longitude. Now everything is fine, but the temporal frequency is the 8 days. I'm gonna convert it to, for example, annual frequency. Let's make a new cell and define a new variable. So NDWI for annual, NDWI with annual frequency equals to get the NDWI data and then resample it to time equals to annual format, year to the yearly. For each year, I'm gonna get the average NDWI during the time. So if you want to get maximum, just enter max. If you want a median, just enter median. It's totally up to you and target of your study. I'm gonna get the average for the whole for each year separately. Let's run a code and make a new one. This is NDWI for annual frequency. Now if you go to the time, you can see we have the average from 2001 to 2024. Everything is fine. And now in the final stage, I'm gonna plot the NDWI variation, the annual average NDWI for the targeted area. Let's call the NDWI annual and plot it. Plot x equals to longitude. We already have longitude. Y equals to latitude. Because it is a two-dimensional plot, we need to define what it is x and what it is y. So for x and for y, the next is color map equals to, for example, blues. I'm gonna have a spectrum of blue colors. The next one is I'm gonna have a grid structure to show each year. So in the grid structure, we need to define a column. The column could be time. The third dimension for the plot is plotting data through the times. So, and call wrap, how many actually image we want to have in each row. For example, I'm gonna have 5. Let's run a code, and after a few moments you can see the final output here. There it is, but something is wrong. It's about some actually outlier values actually cause problem in the output. Normally we expect for NDWI it is expected to have values between -1 and +1, but here values goes beyond. So to solve the outlier problems that's happened because of the outliers, define a new argument as robust. So and let it to true, leave it to true. In this case, we can get rid of the outlier values, and here it is. You can see the contrast is much better than before. So here you can see that most of the values ranges from -0.7 to +0.7. You have each year separately with the blues spectrum that shows how water bodies changes from 2001 to 2024. You can see that as we are going forward, the lake is desiccating more and more until the last 3 years. You can see most part of the lakes unfortunately desiccated, and these facilities recently provided by the XEE library in the Google Earth Engine, and you can use the XEE and array structure to integrate satellite data with array structure and make useful plots. So But the last question is how to get export. If you want to get export with the highest quality, just enter plt.savefig, just like that. Here is lake desiccation, just like that. With PNG format, the output quality 360 is a good item, is a good option for the DPI dot per inch. And the next parameter is BB box inches. In order to have all the parameters, all the figures in a one PNG file, BB box inches must be typed. Let's run a code. Something is wrong. Save fig. Yeah, it was my fault. Save fig. Let's run a code again. After a few moments, go to the local file here. You can see the lake desiccation now created. Let's download it. It's very easy. Just save it into your system, and here you will have a high quality map. You can actually have a little bit zoom to see the quality of output for your study. I hope you like this tutorial as much as I did, and I'm asking you to share this tutorial with the remote sensing community that allows you to have insight about how to deal with satellite data in the Google Earth engine. Thank you for your attention.